Hi there, my name is Shengyao Zhuang. I'm a PhD student from IE Lab at the University of Queensland. This video is about our SIGIR2021 paper, How do online learning to rank method adapt to changes of intent? This is joint work with my supervisor Guido Zucang. In this paper, we investigated an untouched problem for online learning to rank methods. So this figure illustrates a typical online learning to rank system. Where users issue queries to the ranking system, then the ranking system uses the online learning to rank algorithm to retrieve and rank documents. Users then will make interactions with the displayed list. Finally, the ranking algorithm will be updated according to the interaction data. Unlike a classic offline learning to rank, online learning to rank methods aim to train the ranking model from user implicit feedback such as clicks. This is because click data is much easier to collect when comparing with the human judged data used for offline learning to rank. However, clicks are weaker and biased learning signals. For example, higher ranked documents are usually attracting more clicks even they are not relevant. So current work in online learning to rank community are mainly focusing on designing online learning to rank algorithms that can deal with this biased click data. Actually, many methods have shown promising results. In fact, the state-of-the-art method PDGD, which I cited here, can reach the same level performance as the offline learning to rank method. Another interesting property of online learning to rank is that this is a lifelong learning system, meaning that the ranking system will be continuously updated as long as it can receive user interaction data. Based on this property, the community claims that online learning to rank can adapt to changes in user intent, which seems to be obvious, right? As the user click pattern will change with the user intent change. However, these benefits of online learning to rank algorithms have never been formally studied in the literature. Hence, in this paper, we aim to fill this gap. So what is exactly the user intent change problem? We define user intent change as users may change their preferred documents to the same query over time. Here I show an example of user intent change. Users who search for COVID outbreak in February last year are likely looking for news regarding the first outbreak happened in China. But users who searching for the same query recently may actually looking for the documents about COVID crisis in India. So the user intent to the same query changed over time. And of course, people who searching for this query may also looking for information about vaccines, lockdowns. So the user intent is usually mixed. And in this paper, we want to investigate how existing online learning to rank algorithms adapt their rankers to user intent change. In order to investigate this, we have to solve two challenges. First, there is no dataset that has relevant document judgments to different user intent, so that we cannot conduct simulation experiments in an offline manner. It is also impossible to conduct online experiments with real-world users, as we never know the actual user intent. And secondly, there is no evaluation matrix to quantify the effect of the user intent change for online learning to rank. So to solve the first challenge, we created a dataset by adapting an old track collection, namely WebTrack 2009 to 2012. Specifically, there is a relevant document diversity task in this collection, in which the relevance label of each document has been judged according to different subtopics. As an example, here I put one query which is with its different subtopics in this collection. It is important to note that each subtopic to the same query will have different set of relevant documents. So with this collection, we can actually create a dataset with 4 different user intent labels by simply treating the subtopics as different user intent. So now we have a dataset that contains queries and documents with relevant judgments according to different user intent. We then created a learning to rank dataset by extracting features for each query document pairs. Again, for each pair in the dataset, different intent will have a different relevance label, meaning if you change the intent, the relevance label to each QD pair may also change. So following the standard online learning to rank experimental setting, where we simulate real user clicks behavior with click models. These click models simulate user clicks on the displayed list based on the ground truth relevance labels provided in the learning to rank dataset. We use 3 different click models in our experiments. So the perfect click model mimics the perfect user click behavior, where the user will click on every relevant document they observed and will not click on irrelevant document. A navigational and informational click model mimics noisy user click behavior, where irrelevant documents also may have some chance to be clicked. More discussions on these click models will refer to our paper. So because our dataset has different intent labels, we also can simulate user interchange behavior with our dataset. So the simulation procedures goes like this. First, we set a current user intent. Then for each time step from 0 to n, we uniformly sample a query from the dataset and then generate a ranking list according to the current ranking model. Then we simulate the clicks on the ranking list based on the click model and the current user intent. Next, online learning to rank algorithm will update the ranker with the click data it received. Then, if the time step is equal to some point, we then change the current user intent to another intent. This means after this point, the relevant document of each query will also be changed. Hence, the click pattern simulated by click model will be changed as well. By doing so, we can test online learning to rank algorithms with simulated user interchange environment. So to solve the second challenge, which is no measures for interchange effects, we propose 2 novel evaluation metrics for this task. So the first one is called NDCG drop at k. This matrix measures how susceptibility of online learning to rank algorithms at the interchange point by measuring immediate NDCG performance drop after these points. So the second one is called NDCG delta at k. This matrix measures the cumulative NDCG performance gap between the ranker trained with a fixed intent and the ranker trained with the same intent but changed from another intent. Both matrices are normalized, thus their values are always between 0 and 1, and the value is smaller is better. So let's move to the experimental result and key findings. We first discussed the susceptibility of different online learning to rank algorithms to user interchange. The plots in these slides are NDCG learning curves of different online learning to rank algorithms during training. Let's first focus on the perfect click model result. So the dashed lines indicate the interchange points. At the 10th step immediate after these points, we move the current intent to the next intent. The plots clearly show that there are NDCG performance drops at each point. These drops are exactly what our proposed NDCG drop at k wants to estimate. For the PDGD algorithm, the drops are more obvious, which means PDGD is more susceptible to interchange. The drops for the other 2 methods are less obvious, which means they are also less susceptible to interchange. But overall, they are also less effective than PDGD. Although all the methods are affected by the user interchange, it is clear that online learning to rank method can adopt their rankers to user interchange. For the curves of the informational click model, the drops at the interchange points become much less obvious. This means NDCG methods are less susceptible under noisy user click environment. This table also shows the susceptibility of each method estimated by our proposed NDCG drop at k. The value in the table further confirmed the findings we discussed in the previous slides. For the experiments I've shown in the previous slides, the user intents always abruptly change to another intent at the interchange point. However, this will not be the case in the real world. Hence, in our paper, we also investigate different user interchange patterns. So the first interchange pattern we investigate is called smooth abrupt change, which we consider there is one dominant intent at each slot, but mixed with other 3 intents. The colored curve in the figure are NDCG performance if you train the ranker with a corresponding fixed intern environment. And the blue curve is the performance of the ranker trained with the current interchange. So the size of the shade area between the fixed intent and the current intent indicates the total loss of the ranker trained with the interchange environment, which is what our second proposed metric NDCG delta at k trying to estimate. As the shade area show here, the online learning track algorithm is struggling to adapt to the interchange and always underperform the ranker trained with fixed intent. This is expected, as in this case, the click learning signals come from different user intent. Hence, the algorithm will try to learn a ranker that can take care of all the intent, which is a harder task. The second interchange pattern is called intent leaking, where the current intent gradually changes to the next intent over time. In this case, the learning curve of the current intent is much more smoother than others, which is also expected as there is no abrupt interchange points. But still, the ranker trained with current intent is always underperform the ranker trained with the fixed intent. The last pattern we investigated is abrupt swapped, which here we also abruptly change intent, but the intent only change between the two intent. Well, we're interested to know if the online learning track algorithm can quickly adapt to the intent it observed before. First, in this case, we notice that the algorithm cannot adapt to the same performance level for the second intent that is observed during this training, even we give it a long period of training time. However, for the intent that the algorithm observed before, which is intent 1, it actually can adapt to the same level of performance. These findings show that online learning track algorithm cannot completely adapt to another new intent, but can easily adapt back to the intent it observed before. We also did the same experiments, but this time we swap more frequently in a shorter period of time. It seems that online learning to rank is easier to adapt to the intent that it first observed, which is intent 1 in this case. This result also can be confirmed by our proposed NDCG delta at k. To conclude our work, we formally investigate how online learning to rank method adapt to user interchange. We created a new dataset with intent labeled, which allows us to simulate different user interchange behavior. We proposed 2 novel evaluation metrics for online learning to rank in order to quantify the impact of user interchange. With our new dataset and the new evaluation matrix, we tested different online learning to rank algorithms under different interchange patterns. The key takeaways message from our paper is that we confirmed the claim made by the community that online learning to rank method can adapt to user interchange, but different algorithms perform differently under different interchange settings. This finding suggesting that you should study this property for your online learning to rank algorithm. More information about our work, such as code and dataset, please check out our website. Thank you for listening.